I'm going to look at a problem that will require us to derive an equation to solve it. And the equation is sometimes called the range equation. And the reason it's called the range equation is it is able to solve for the horizontal distance that a projectile travels. Remember that the horizontal distance is sometimes referred to as the range of the projectile. So the question might take the form of this. What's the range of a projectile that is launched at an angle of theta? So we don't know a specific number, it's just called theta, with an initial velocity of v0. We're going to assume that the projectile is launched and lands at the same height. So as soon as you see that, you're going to say, okay, same height, delta y is going to equal 0. Okay? So as soon as you see that, you write down delta y is 0. And the other given information will start on the next page. So I've got delta y is 0. I've got angle of theta. And I know that my initial velocity is v0. I guess I also know my acceleration is equal to g in the y direction, right? So I know that information, and I'm trying to solve for delta x. That's what I'm trying to solve for. A problem might be something like a golfer launches a ball at 45 meters per second at a 30-degree angle. How far does it land down the fairway? Or a punter punts the ball with a certain velocity at a certain angle. Where does it land? So those are range type questions. And it seems like you don't have enough information to solve this because you're only given some basic information. But what we're going to do is we're actually going to be able to derive an equation here that's really simple. Okay? We're going to start by considering the x direction. And the only equation that we ever need to use in the x direction is our constant velocity equation that looks like that. Now, in the x direction, I don't have a velocity in the x direction, but I've got an initial velocity and an angle. So if you can picture this, it's like the projectile is launched at an angle theta with an initial velocity of v0. So going back to our knowledge of vectors, we know we've got two components here. We've got a vx and we've got a v0y. So vx in terms of v0 and theta is pretty simple. v0 times, since it's the adjacent leg of this angle theta, it's cosine of theta times the hypotenuse. v0y is just equal to the sine of the angle, since v0y is equal to it's the same length as the opposite leg of this triangle. I could show v0y over there if I wanted to. So that's going to be v0 times the sine of the angle. So I'm going to use these trig relationships here to that expression of the x and the y components of initial velocity and substitute them into my equations up here, starting with the x direction. So what I'll do is I'll say vx, which is really v0 cosine theta, equals that range delta x over the time. And you'll see all I've done is I've substituted that expression in for vx. Well, in the y direction, I've got a different equation that I'm going to start with. I'm going to start with my invisible woman. Okay, that's the invisible woman in the y direction. And I know that the delta y in this case is 0. And I've got an expression for v0y right here. So I'm going to substitute that in right there. So since I'm running out of space here, I'll take this to the next page. So I've got delta y we've got that as 0, and v0y was v0 times the sine of the angle, if you remember. Okay, so substituting all that in, I get this in the y direction. Remember, in the x direction, I had, from the previous page, I had v0 cosine theta equals that delta x, the range that I'm trying to solve for, divided by time. Okay, so here's the issue, is that I don't have the time interval, and it's an unknown, so I've got to get rid of that out of the equation. So what I'm going to do, what I'm going to have you guys do, is I'm going to have you solve for the delta t in the x direction. So isolate the delta t over here all by itself. Use the expression that you get in the x direction for delta t and substitute it in the y direction for the delta t over here. Substitute in your g in the negative y direction for acceleration and get an expression for delta x. So basically, you're going to rearrange the resulting equation where you combine these two together, solve it for delta x. And the last hint I'm going to give you is there is a trig identity that I don't expect you to know. If I asked you this on a test, I would provide you with the trig identity because I don't expect you to memorize trig identities that will make the equation easy to solve. So here's the trig identity down here. You'll probably end up, or you should end up, with this expression in the equation once you combine those two equations to eliminate time, and substitute in for this on the left side, this on the right side, because they're equal to each other. All right, so you can substitute in sine of 2 theta for 2 sine theta cosine theta. Turns out they equal the same thing. That way you get rid of these two trig identities and you have only the sine identity, or the sine function, in your answer. So it makes it easy to calculate if in different circumstances. All right, so I'm going to ask you to finish this derivation following the steps that I just gave you after I got you started, and we'll talk about this on our Zoom class meeting. Okay, I will see you on Zoom.